Hi, my name is Shaya Wolf, and I'm presenting on an attack against machine learning models that I worked on for the Cedar Lab this past year. This work was accomplished under Dr. Mike Borowczak and was inspired by Rita and Haile at Idaho National Lab. To start with, our central research question is concerning the trustworthiness of machine learning models, and to do that, we commonly look at different attacks. So this first example here would be an example of an attack where you add an adversarial perturbation to an image, and even though that image looks the exact same to the human eye, to a machine learning model, you'll get a different result. So a yield sign instead of a stop sign. In the second example, it's actually the opposite. So you have patterns that actually mean nothing to a human, but to a machine learning model that is very confident that it is something else. And then the third example here just being a real world example of insurance fraud, a case where their insurance should have been denied but it was instead approved, or vice versa. This background stems off of the machine learning pillars that were created at Idaho National Lab thanks to Rita. It starts with things like the purpose and relevance, making sure that your model matters to other people and the problem you're solving is interesting. But then from there, we really build on with a ton of data and really considering every aspect of that data. Transfer learning is another concept we'll need today. Consider that you want to build a model to tell apart different types of flowers, or to determine if you have a certain type of cancer or a brain tumor. Generally, you don't want to have to start from square zero in training those. A lot of different models have been trained on image data, so they already know things like what is an edge, what are corners. So instead of recreating that wheel every time, people commonly use pre-trained models. Most commonly in academia, it'll be this ImageNet model, trained on thousands and thousands of image data, and it saves you computation time and money on the back end. So what we're going to do is look at an attack based off of this paper, Backdoor Attacks Against Transfer Learning with Pre-trained Deep Learning Models. And essentially what that is somebody who's taken a pre-trained model, but accidentally taken a falsified version of that model. So something that looks almost the exact same as the regular model, almost imperceptible without advanced data analytics. And they're going to even fine-tune it on their own data. Say they have flower data, or they have that patch chameleon data set for cancer detection. They're going to take their fine-tuning data, and this attack is still prevalent throughout that throughout their training. So as an example here, as just like an attainable example even, we were just looking at like flower data. So say a user is able to get their ImageNet data and their fine-tuning data, say in this case it's a bunch of flowers, and they accidentally pull the wrong pre-trained model from an adversary. It looks the exact same, it has almost the exact same weights as the regular model. However, once they fine-tune their model, in very specific cases that are created by the attacker, an image that's sent through that fine-tuned model will be inaccurate. So in this case, a rose versus the output of a sunflower. There are a couple of different types of models, so it's not dependent on which data set you use. So we looked at 3 of them. VGG16 is the one here on the left. The top one is Inception V3, and then the bottom one is ResNet 50. They're all just different ways of looking at image data. So we wanted to show that this attack is model agnostic. There is the perturbation type that was used in the original publication. The biggest weakness here is that if you're actually looking at this triggered data, a human eye can tell that as a trigger. So what we wanted to do is advance this attack using a much stealthier trigger in the data so that it can blend in a little bit. And then actually, to be fair, so we're looking at like VGG16. After pre-processing, this is actually what your adversarial perturbation would look like, because it doesn't take RGB in that order. So you get a blue golden retriever, a Bluden retriever, but the point is that your machine learning model is still quite confident that is a mosquito net. So the next thing we need to do is baseline our model, where we get about a 65% accuracy. Now we want to maintain that accuracy so that we're not drawing any flags, but we want a lot of our triggers to successfully get the wrong answer to show that the attack, even if it doesn't affect the overall accuracy, we have a really good chance of having a trigger that is effective. In this case scenario, we find that even after fine-tuning, you get 50% of your triggers succeeding, meaning that even if you fine-tune this this model on new data, on fresh data, on your data, the attack still perseveres. Also, it also survives pruning defenses, meaning that if we prune off individual nodes and we retrain those from scratch, you still have just a slight drop in the effectiveness of the triggers because the other weights are able to pull it back up. And then lastly, we proved that it also survives dropout layers. So just dropping entire layers of your network or whatever your model looks like. We have definitely a larger drop in triggers, only 43%, 44% effective versus 50, but that's still above a 1 in 3 chance, right, that you're going to have an effective trigger. And if you can sneak one image into a data set, you can likely sneak 3. So for future work, we're looking at improving the trigger by generating multiple versions of the triggered image to get a higher percentage of effective triggers. Next thing we're looking at is creating new versions of the attack by assuming different knowledge of the fine-tuning data. And then also we'd like to extend it to other models and data sets. So in the poster, you can see that we've already benchmarked those models on all the different data sets. That's a huge part of the battle. And then most importantly, generating a full defense to this sort of attack. Thank you. I hope you enjoy the poster symposium.